Human beings have always used drugs of all kinds, for medicinal purposes or for pleasure. Alcohol, cocaine, morphine. The place where all drugs act is in the brain. Biology is now able to explain how they work inside of our heads, while research on drugs has enabled science to better understand how the brain itself functions. Opium and its derivatives, like heroin and morphine, as well as tranquilizers prescribed for medical reasons, help relieve pain and stress. But these drugs are also highly addictive. Opium, extracted from the juice of the poppy plant, is one of the world's oldest drugs. It is mentioned as a treatment for pain, insomnia, or as a cough suppressant in Middle Eastern and Egyptian texts written several thousands of years ago. Heroin, a more potent derivative, is processed from opium. A simple recipe, used in Afghanistan and Burma, the main opium-producing countries, consists of mixing opium paste with a few ingredients such as water, lime, and ammonium chloride to transform it into 80% pure heroin.
Ça peut vous faire plaisir.
Ouais.
Hein?
C'est un vieux truc. C'est long, c'est loin tout ça. Elle est belle, hein, c'est
merveilleuse ivoire.
C'est l'ivoire.
Avec une patine. Et celle-là qui est encore plus extraordinaire, qu'un connaisseur comme vous appréciera, avec le téton.
Le téton,
en embout.
Ouais. J'étais bien jeune, vous savez. Bon, il y a le décor est très important, il y a la lampe, il y a le grésillement, il y a la boule, la petite boule qu'on fait. Puis alors, il y a longue aspiration, et toutes les portes de la communication s'ouvrent. On obtient une espèce de dilatation de l'encéphale, il y a une espèce de prurite cérébrale, surtout au début, c'est merveilleux. Cette espèce d'envahissement total qui vous arrive de partout, qui vous prend dans les orteils, qui vous remonte des orteils au cerveau. C'est une invasion. La fumée, c'est absolument incroyable.
Satan qui quitte, Satan qui quitte, Satan qui moise, dans Prairie pour les 12 yeux, mais c'est moi qui l'aime le mieux.
Alors à Saigon, on voit là la manufacture d'opium, parce que tout l'opium appartenait à la régie et était vendu par la régie. On était sûr de la bonne qualité et l'État prenait sa part au passage.
The addictive practice of smoking opium was relatively uncommon until colonial administrators forcibly legalized the opium trade in the 19th century, making it massively available everywhere in Asia. From the tincture of opium sold in pharmacies to the proliferation of semi-illicit opium dens, addiction soon spread to Western countries, and the drug was banned after 1910. As for heroin, abuse became so problematic that it was outlawed a few years later. The law then came down on morphine, a potent and highly addictive painkiller, which was restricted to medical uses. Today, 16 million people take opium-based drugs. Morphine is legally prescribed in hospitals as an analgesic to relieve pain, while over 10 million addicts use heroin, the most habit-forming of all drugs. Psychiatrist Marc Valeur runs a medical center which offered one of the first treatment programs for drug addicts in Europe 30 years ago.
Although there are thousands of highly potent psychoactive substances, why has this specific product, heroin, diacetylmorphine, become the antisocial, the dropout drug, the drug addict's drug? Opiates are clearly the most extraordinary of any of the anesthetics we know of. They are also the most extraordinary of analgesics. Heroin, like morphine and opium, has a soothing effect on everything that is felt by the subject, on both external sensations and internal sensations. All pain, all suffering is relieved, physiological, physical suffering, as well as mental suffering, depression, anxiety, etc.
Since Thomas de Quincey came out with his Confessions of an English Opium Eater back in the 19th century, many others have written about their life under the influence of drugs. In 1961, the Scottish novelist Alexander Trocchi published a book about his life as a heroin addict, which inspired the American channel NBC to film him in action.
Well, I'm going to take a shot now just to show you what it's like. In America, I've seen people take overdoses and come very close to death.
Alexander Trocchi died of an overdose at the age of 60.
It's my hope that neurobiological and psychological models of dependence will enable us to rethink, in a much more global way, all the problems related to mental suffering and psychological disorders. I think these approaches will enable us to revolutionize psychiatry. We'll have a more dialectical vision in which physiological dependence and psychological dependence will be able to mutually explain each other. I think we'll finally have models in which psychological approaches and physiological approaches will complement each other dialectically, will intercommunicate, respond to each other, and together they will lead us to a better understanding of all mental phenomena in general.
Studying the psychoactive effects of drugs would not have been possible without rats or mice. They share many of the same genes as human beings, and drugs stir up the same kinds of tempests in their brains. In fact, all of humanity is morally indebted to these little creatures. We can intoxicate rats, manipulate their genes, even cut them up into little pieces. This is the terrible but necessary task of laboratories that compare drugged or genetically modified rats to normal or control rats. Like all drugs, heroin, seen here in crystal form, and other opium derivatives work by hijacking the brain's communication system. Our brain indeed spends most of its time chatting to itself. In order to keep things running, it relies on a network of ongoing conversations between our 100 billion nerve cells, or neurons. The neurons exchange information by sending each other chemical messengers called neurotransmitters. Whether it has to do with pain, pleasure, or the rate of information exchange, the neurotransmitters act as regulators, maintaining a complex and fine-tuned equilibrium which is essential to all of our bodily functions. Between the neurons are little spaces which are always busy with activity. It is here in the synapse that the neurotransmitters do their work. They transfer information from one neuron to the next by binding themselves to the appropriate receptors. In 1973, it was discovered that morphine, like heroin, was able to bind to some of these receptors. This was a major discovery that prompted scientists like Bridget Kiefer to investigate a system that is essential to the functioning of our bodies.
After this discovery, we of course supposed it would be rather odd for nature to have endowed us with receptors specifically made to receive a molecule produced by poppies. That didn't make any sense. So that made us think that the brain must naturally secrete some molecules of its own that, under certain physiological circumstances, would habitually interact with these receptors. And that's when we started looking for the body's own natural activators of those opiate receptors. After the first peptides were discovered, we found a family of peptides which were given the name opioid peptides, molecules that are the endogenous activators of these receptors.
Because of their resemblance to opium-based drugs, these molecules were given the name opioid peptides. These peptides and their receptors make up what is called an endogenous system. Endogenous because it is inside our bodies, and this system is vital to our existence.
The endogenous opioid system is activated, is mobilized in stressful or painful situations. By releasing the opioid peptides and activating the receptors, an anti-pain effect is produced, which will enable the organism to cope with the situation, to deal with the danger.
50 years ago, Manchester may well do today. Void out to govern.
All mammals, including football players, have an opioid system.
And I think Trotman's hurt. Yes, and so's Murphy.
During the FA Cup final in 1956, Bert Trautmann, the Manchester goalkeeper, was knocked down and broke a vertebra in his neck.
Well, now, it's obviously not his head, but his neck.
It was so painful that he should have passed out. But in the heat of the action, his opioid peptides kicked in and minimized his suffering. He got up and played until the end of the match.
By 3 goals to 1.
Trautmann became a national hero, and it was the first time an opioid system was awarded Footballer of the Year. The opioid peptoids in the goalkeeper's brain activated their receptors in the areas that control feelings of pain. The spinal cord, first of all, which transmits all sensations felt by the body to the brain. Then the brainstem, which handles vital reflexes and automatic functions like breathing and heart rate. Finally, in the limbic brain, where the striatum, the nucleus accumbens, the thalamus, and the amygdala regulate emotions such as fear and anxiety, or feelings of pleasure and reward.
When morphine is administered to someone, it floods the nervous system and activates all the receptors everywhere at the same time. That's not at all a natural process. Under natural conditions, a painful or stressful situation will usually activate specific circuits and trigger the release of enkephalins or other opioid peptides at certain synapses and in certain areas of the brain. The effect is thus much more limited.
When morphine and heroin inundate the brain, they don't just suppress pain, they also slow down the flow of information by acting on the brain's braking system. This system is controlled by a neurotransmitter called GABA. GABA is a speed moderator. Under normal conditions, its job is to inhibit the neurons and slow down the dispatching of messengers around the brain. Morphine and heroin prevent GABA from accomplishing its mission. GABA is unable to restrain the release of dopamine, a neurotransmitter that plays a crucial role in feelings of pleasure. An outpouring of dopamine thus floods the neurons, and this is what produces the rush of pleasure provided by heroin. This process occurs in a very specific place in the brain, in the area around the striatum, and especially in the nucleus accumbens, which we now consider to be the pleasure center of the brain. All drugs, in fact, generate a huge increase in the amount of dopamine in this tiny area. Emiliana Borelli studies how all these mechanisms impact the functioning of the brain.
Studies done on animals have shown that the rise in dopamine levels could be linked to the feeling of pleasure. And so it's this feeling, the feeling we have when we take the drug, and which is caused by dopamine, that makes us want to keep on taking the drug. And that could be the first step towards dependence.
These pigs are on their way to addiction. By indulging in this strange activity, battery pigs create a constant low-level pain in their jaws. It is a way of simulating their opioid system and anesthetizing their stress, a habit which could become addictive.
In fact, it's because this system involves both the pain and the reward pathways that the major exogenous opiate, morphine, has two very powerful effects. It's a very strong analgesic, and it's also highly addictive precisely because it works on both levels. It affects both types of circuits.
Brigitte Kiefer thus decided to try and separate the anti-pain effect from the addictive effect of morphine. To do so, she studied the three different opiate receptors, mu, delta, and kappa. To find out if one of these receptors was responsible for addiction, she eliminated the respective genes that produce them in mice, in genetically modified mice called knockout mice.
We created mice in which the gene of each receptor was removed, one mouse per gene. And in the end, it was the mouse without the mu receptor gene that showed us that it was the mu receptor that mediated all of the effects associated with morphine. We observed that without the mu receptor, morphine was no longer analgesic, no longer addictive, and no longer produced respiratory depression. We tested all of the biological effects of morphine and found that none of them occurred anymore. However, the morphine continued to work very well in the mice without delta or kappa receptors. It was thus through an A-B demonstration that we discovered that it was the mu receptor that mediated all of the actions associated with morphine. But it also meant that it would be impossible to separate the analgesic effects from the addictive effects via two different receptors. So in terms of therapeutic strategies or designing pharmaceuticals, if we want to create a mu activator, it will inevitably be an addictive analgesic. That was the conclusion of the study.
When the drug launches its offensive on the brain, it sets off an entire chain of complex mechanisms that affect biological as well as psychological processes.
There's a huge difference between dependence, in the sense of having a physiological need for a substance, and addiction, in which the substance at a certain point becomes the entire focus of the subject's life. Physiological dependence can be compared to the type of dependence a diabetic has with regard to insulin, the same sort of dependence we all have with regard to food, to water, etc. In other words, a dependence which is physiologically very demanding, but psychologically neutral. You can take insulin every day without living your life solely as a diabetic. You can be a doctor, a teacher, a father, a mother, and a diabetic as well. A heroin addict, however, wakes up as a heroin addict and cannot be anything else because the social and psychological demands connected with procuring heroin are just too overwhelming. One general theory, which may explain why people take this substance, has to do with the act of self-medication. We're dealing with subjects who have problems, who experience traumatic events in their childhood, who have deep narcissistic flaws, who have experienced what Olivier Stein called the broken mirror, often deep-rooted traumas from childhood or pre-adolescence. Heroin provides them not only with a source of pleasure, but with a wonderful medication for all their existential suffering. Gradually, however, this medication and source of pleasure become nothing more than a source of dependence. What was at first a marvelous love-at-first-sight romance between a person, an environment, and a substance becomes a purely biological process of dependence between the subject's body and a substance. The etymology of the word addiction is in fact quite interesting. As the psychoanalyst Jean Bergeret pointed out, addictus in Latin meant bondsman, a slave bound by debt. So addiction might be a way for some people to pawn their bodies in order to pay off a debt from the past, from their childhood, which has remained unpaid, a way of turning oneself into one's own bondsman.
Ironically, the only relief from his demons is through the very poison that originally hooked him. The same heroin that will bind him ever more tightly to his living hell. But the blessed temporary delivery is not given through any noble, charitable motives. It's just the final step in Pete's carefully laid plan. He's made another junkie and another source of money.
We are still far from understanding the mechanisms underlying dependence on any kind of drug. Researcher Pier Vincenzo Piazza wanted to find out if anyone could become an addict or if addiction was actually an illness.
In our society, drug addicts are increasingly considered to be people who are either bad or sick or somewhere in between. For social reasons, I think it's extremely important to be able to answer the question, is there a difference between a depressed person who, in fit of depression, kills 15 people and is sent to a psychiatric hospital, and a drug addict who steals 2 skirts and 500 euros and is sent to prison? Is drug addiction a pathology or not? One way of trying to answer this question is to say, does drug addiction exist in animals? Because if it does, that means that this type of pathological behavior can exist outside of any social context and is not specific to any particular species, in which case it's probably not a vice but something else, a true behavioral pathology.
In 2004, Dr. Piazza's research team conducted an experiment to find out if all rats responded in the same way to drugs.
You can't take 300 human beings, shut them up in a walled city somewhere and give them free access to a drug in order to see who becomes addicted and who doesn't. But you can use animals, a homogeneous group of rats, for example, and give them a similar kind of access to drugs in order to see which ones learn to self-administer the drug and which ones don't.
Dr. Piazza thus adapted the defining characteristics of addiction to laboratory rats. His main resource was the Diagnostic and Statistical Manual of Mental Disorders, or DSM-4, a major reference book used by psychiatrists. The first characteristic of addiction is devoting a large amount of time to procuring the drug and the inability to limit intake. The researchers thus taught the rats that they could only get the drug at certain times of the day. When the drug is no longer available, a normal rat soon stops seeking its dose. The addicted rat, however, keeps on demanding its fix regardless. It can't stop. The second characteristic involves the degree of motivation. Drug addicts will go to extraordinary lengths to obtain their drug. The researchers thus increased the number of requests the rats had to make, 800, 1,000, and even up to 2,000 times to obtain a single dose. After 100 or so requests, the normal rat decides enough is enough. But nothing can stop the addicted rat, who will wear itself out getting its dose. The third and last characteristic: an addict will continue to take the drug in spite of harmful consequences. This time, whenever the rats sought a dose, they received a small electric shock. A normal rat is not willing to sacrifice its little body for the drug. It stops immediately. The addicted rat, however, stoically and stubbornly endures the electric shocks. The conclusion of the experiment was that all rats do not respond equally to drugs. Some become addicts, others don't.
What's interesting is that the percentage is about the same as for human beings. Among human beings, depending on the drug, the percentage between users and addicts is from 10 to 20%. And among the animals, we found that 17% of the group showed those characteristics of drug addiction.
This man came to Switzerland when he was 44. This one at age 16. This one at 37. And this one at 63. This one left it when he was just 18.
You are really and truly addicted when you realize yourself that it's become a problem, when it becomes a source of suffering. You want to cut down or stop using the drug, but you can't. That is the true defining characteristic of addiction, wanting to stop and not being able to.
I think it's the same for depression. The main causes of depression are moving away and divorce. That's what reactive depression is. But we're not going to eliminate moving or divorces in order to keep someone from becoming depressed. We try to cure the depressed subject. Limiting the availability of drugs is, of course, important, and it should be done. But that's not how we're going to solve all of the problems of drug addiction. Drug addiction is really a medical problem. And just as with depression and other psychological pathologies, it's by understanding the mechanisms that underlie these disorders and trying to reverse them that we'll get to the heart of the problem.
Certain types of medicines also lead to problems of dependence. In general, those used to treat anxiety, but in a less radical way than heroin. Sedatives such as chloral, high-powered barbiturates, or those containing meprobamate lead to severe dependence and are rarely used nowadays. For anxiety disorders, doctors today prescribe tranquilizers such as Valium, Xanax, or Lexamil, collectively known as benzodiazepines. In patients suffering from anxiety disorders, certain areas of the brain, such as the striatum and the hippocampus, are affected. The main target of pharmaceuticals, however, is the amygdala, which triggers reflexes related to fear and anxiety. For a long time, scientists had no idea exactly how benzodiazepines interacted with neurons. Dr. Hans Moeller, a renowned specialist in anxiety disorders, was the first to find out.
Normally, anxiety is something absolutely essential for everybody. We would have died out in the meantime without anxiety. Nobody could cross the street. So anxiety is absolutely essential. But there are patients who suffer from an excess of anxiety. I don't know whether you have ever seen a patient with a panic anxiety attack. It's absolutely frightening. These people sit in a restaurant or in the office or at home, and suddenly, without a clear trigger, they suddenly freeze, they sweat, their heart races, and they think their last hour has come. They cannot move, they cannot get up, and after about an hour, the attack disappears or slows down. So anxiety in these patients is devastating, and one has to find a way to help these patients.
Hans Möller discovered that benzodiazepines like Valium act on the brain's braking system, the GABA system. In an anxious person's brain, GABA has a hard time slowing down the flow of information. Benzodiazepines jump in and act like a handbrake when the system goes out of control.
What the drugs do, they act like a servo mechanism in the brake of a car. So they enhance the brake system, the inhibitory system. And the drugs cannot activate the brake. It's when you're driving a car, you activate the brake. But the servo mechanism makes the brake more efficient.
Under normal circumstances, GABA activates its receptors and reduces nerve activity in the brain. When benzodiazepines bind to a little spot on these receptors, GABA becomes even more effective, and anxiety messages are completely blocked. Indeed, benzodiazepines are so effective that some people find it hard to do without them.
Certain patients also show dependency. They have problems stopping the medication. And that's why one should normally treat patients with benzodiazepines only for a limited period of time. And one should not treat patients with a history of drug dependence. Somebody who has problems with other drugs or with alcohol should not take a benzodiazepine because the likelihood that they get dependent on benzodiazepines is higher.
At 80 million boxes a year, the world's biggest consumers of tranquilizers are the French. To try and solve the problem of dependence, Hans Möller, like Brigitte Kiefer, decided to examine the role of each of the GABA receptors.
Then we and others found that there are more than a dozen different types of brakes, sub-brakes, so to speak. All are different GABA receptors. Originally, one thought there's only one. It's always the same in the brain. Well, that's not true. There are certain parts in the brain which have this one, others have this one, or this one, or this one. And the classical benzodiazepines, which are now in clinical use, they don't see the difference. They interact with all of them. And we thought, wouldn't it be sensible to develop an agent or a drug which interacts only with these, or with these, or with this one and this one? Perhaps we get rid of the side effects, perhaps we get a different pharmacology. And that is the development which is ongoing at the moment.
Catherine, St. Paul. Yeah, exactly. This is,
Oh, this. Sit down, man.
Until the new generation of tranquilizers arrives, however, patients shouldn't stop taking their pills from one day to the next. For, as with heroin, the body gets used to the medication and starts to need its dose. Without it, it suffers withdrawal symptoms.
Trust me.
The first smoke of heroin can make you throw up, but some people still go back for more. If you get into it, your looks will start to go, and you'll feel even worse.
Once the body becomes used to the drug, we have the same situation as the heroin addict who comes to us for help and says, I started taking heroin because it gave me so much pleasure. It was extraordinary, even more orgasmic than an orgasm. It was fantastic because it made me forget all my existential problems, all of my worries disappeared, all of my suffering disappeared. But now I take heroin just to feel normal. If I stop, I'm in terrible pain. And the pain is both psychological, all of my anxieties return, I can't sleep anymore, as well as physical. I hurt all over. My muscles hurt, my bones hurt, I have diarrhea, vomiting, etc.
He needs a shot now, and he needs it badly. But this is the last one. After he's feeling better, he'll quit. Never touch the stuff again. At first, it all seemed like such harmless fun. It was hip to go along with the gang. But where's the gang now? Why aren't they with him when he needs them most? Too late, he realizes that by joining to belong, he's more alone than ever. This is the one trip he must take all alone. Only he himself can experience the unbearable agony of withdrawal. Alternately, he will feel chills.
Addicts owe these unpleasant withdrawal symptoms to their brain. In order to keep functioning normally, the brain is forced to rewire and readjust its circuits.
6 to 72 hours, then continue for 2 more weeks. In the meantime, he must obey the rules of the drug addict's world of secrecy.
The first time you take a drug, what you experience is just an overstimulation of those neurons. But with someone who continues to take the drug, who becomes a chronic user, what happens is that the cell acquires a sort of cellular memory. It's not only one's personal memory that is involved, but the memory of the neuron itself. In fact, your brain becomes dependent. That is, the brain of someone who becomes dependent, who is a massive and continuous consumer of drugs, changes and enters into a state that we call a state of dependence. It's a state in which the brain becomes used to the presence of the drug and tries to compensate for it by producing an opposite response. Since opiates, for example heroin, inhibit the neurons, if they're constantly being inhibited, after a while these neurons will start developing compensatory responses that will lead them to pump up their excitatory systems. As long as there is heroin in the brain, it will continue to have an inhibitory effect, but the brain will gradually try to get back to a normal state by reaching a new balance. It will thus overcompensate in order to reverse the action of the drug. What happens if the heroin is suddenly removed? The brain is then plunged into a completely different state in which the previous balance is once again altered. Since the inhibiting drug is no longer there, all of the excitatory effects will be unleashed, and that's what causes the withdrawal symptoms.
Different kinds of treatments now exist to help addicts quit heroin without suffering from withdrawal symptoms. Since this distribution program was initiated in a New York prison in the early 70s, the use of synthetic opiates has become widespread. Methadone and buprenorphine, better known as Subutex, substitute for heroin in the brain, but are gentler on receptors. They are thus called substitution treatments.
Methadone enables addicts to avoid withdrawal. The receptors continue to be occupied, so there are no withdrawal symptoms, and thus no compulsive drug-seeking behavior. You're in a relatively stable state, which means you can function pretty normally in society. At the same time, however, you're just as dependent on methadone or buprenorphine. Only you don't get the rush or the high that heroin gives you because methadone and buprenorphine never reach the levels that trigger that effect, which is sought by addicts.
On a purely physiological level, we could say that by substituting methadone or buprenorphine for heroin, we are merely substituting one drug for another. We are substituting a legal drug for an illegal drug, a very expensive drug for one provided by society. And we are replacing a substance that has a violent short-term effect with substances that are less violent and longer-acting.
But substitution treatments are not the ultimate solution. Researchers would like to develop treatments that cure addiction rather than just tone it down. In order to do so, scientists are taking a closer look at dopamine, the neurotransmitter linked to the pleasurable feeling produced by drugs. As with opiates and GABA, there are several types of dopamine receptors. One of them, the D2 receptor, seems to play a key role in drug addiction. Researchers used genetically modified mice to study this receptor.
In order to study the role of D2 receptors in drug response mechanisms, as well as its physiological function in vivo, we created knockout mice whose D2 receptors were suppressed.
Dopamine regulates a variety of physiological functions, including movement. This strange machine is used to test motor coordination. A complete failure for the knockout mouse. But D2 receptors also play a role in drug addiction.
We were able to show that mice without D2 receptors no longer respond, for example, to the reinforcing effects which eventually lead to addiction. Other laboratories have done studies on this subject. They found that among animals, as among humans, some individuals are more prone to drugs than others. This clearly depends on the individual makeup of each person. All of us probably have different amounts of dopamine or neurotransmitters. Genes are expressed differently in each individual. None of us are alike. So, for example, I might have a lot more D2 receptors than somebody else, and so I might not react in the same way to a drug as someone else.
Nora Volkow is the director of the U.S. National Institute on Drug Abuse. She has discovered that drug addicts have fewer D2 receptors, and inversely, that people with higher levels of these receptors have an aversion to drugs.
It's a very important question whether the reductions in D2 receptors that we're seeing in people that are addicted are a consequence of repeated drug use, or whether they reflect the fact that these levels were low, the receptors, which make them more vulnerable to taking drugs. As a result of all of these studies and the data also out there from others, I've come to my perspective on this is that having high levels of receptors, of dopamine D2 receptors, protects you against taking drugs. It's a protective factor. If you don't have that high levels of receptors, then you are more vulnerable for taking drugs. And that could be a wide variety of reasons.
This presents a real challenge for science. How can we change the number of D2 receptors without upsetting the brain's equilibrium?
I actually like that interpretation because it challenges us to develop strategies that will allow us to increase levels of receptors. And if you had asked me that, say, 3 years ago, I'd say, well, no, it's not possible to increase levels of receptors right now in humans because we don't have the medicines. What we can do, what I'm actually trying to develop, is the thinking of behavioral interventions, psychotherapeutic interventions that may change, that may increase the levels of receptors. Now you say, this sounds like science fiction. But if we know, for example, that stressors, certainly in rats, chronic stressors, lead to decreases in dopamine D2 receptors, what would be the effects of giving an intervention to a person that's under stress that will relieve that stress?
Back in the 60s, the American soldiers who went to fight in Vietnam became hooked on heroin. It was good quality heroin. They took it for a very long time, and as a result, they became severely addicted. So Nixon's government set up methadone programs and detoxification centers for the soldiers. As it happened, however, the vast majority didn't have to go through these programs and stopped taking heroin on their own. The best treatment, the best method for getting the soldiers off their habit was to end the Vietnam War, to bring them home.
Taking drugs is a very impacting, very powerful experience that leaves a sort of indelible mark, a mark that in addition is strongly connected to a specific environment. Any doctor will tell you that all drug addicts have a very hard time returning to that environment because they will immediately start craving the drug. So it has to do with a process of memorization. And there are studies being done today that are trying to elucidate this aberrant form of learning that occurs when one becomes dependent on drugs.
It's been proven that one of the treatments that works for heroin-addicted laboratory rats is to change the cage. When they're put in a bigger cage with better living conditions, they stop self-administering heroin until they die. These are important clinical findings that have been scientifically validated.
Like drugs, life experiences and memories pass through the neural membrane, the liquid between the synapses, and are forever embedded in our brain. The study of these complex processes has brought neurobiology and psychology closer together.
Dependence is thus physiological as well as psychological. We now look at addiction in a more global way and think that it was probably a mistake to separate psychological dependence from physiological dependence. We've moved beyond the time when we thought of the soul as a distinct organ in the body which was linked to the brain via the epiphysis. We know that psychology and physiology are two ways of approaching the same phenomena.
Let me just give you an excellent example from a study that was just published recently by Michael Meany, where he shows that in rats, when the mother does not have close physical contact with the rat, that leads to a silencing of a gene that makes that animal much more sensitive to stressors. Now, here you have the psychological construct of the response to a stressor, but you have the high advanced information from science identifying that an environmental stressor is silencing a gene that then translates into the lack of an expression of a receptor. So I don't view it as going back to psychology. I'm viewing it as taking advantage of the science and technology that is coming to try to understand what are the neurobiological processes that underlie psychological mechanisms.
It's like a mirror image, in fact, depending on how you look at it. On the one hand, you can say that your genes won't react in the same way to drugs depending on the environment you live in or the experiences you've had. On the other hand, you can say the environment won't affect subjects in the same way depending on their genes. As a result, genes and environment shouldn't be seen as two distinct variables that each contribute 50-50, but as a single influence. And it's the interaction between these two factors that determines who you are.
Stories of addiction are like love stories. One day, someone with a specific set of genes meets a drug. A destructive romance ensues, in which life experiences and psychology play a determining role. These factors are interconnected and unique for each individual, which means we will not all respond equally to drugs. In addition to exploring the mechanisms of addiction, researchers are also interested in learning how the ups and downs of life can affect brain chemistry and genes. Addiction, they now believe, is a disease of the brain. In their quest for new treatments, scientists are tackling the very causes of drug addiction itself.